Good morning. My name is Procópio Stein, and unfortunately I could not be present at this conference, so I created a video about my work. My work is entitled Navigating in Populated Environments by Following a Leader, and that's a work that has been done together with Vitor Santos, Anne Spallanzani and Christian Logier, both at the University of Aveiro in Portugal and at INRIA-Rhône-Alpes in France. The objective of my work is to improve robot navigation in populated environments. In these environments, the robot must be able to interact with humans, to respect social rules, to adapt to the environment, and to navigate safely. Some difficulties of navigating in this environment is that the robot must be able to detect moving persons because they may invalidate the robot motion plan. Reference features as roads and wall may be occluded, and the robot must be able to understand and respect the social interactions of persons. Examples of these environments are shopping malls and also airports. Some previous approaches in this area of dynamic environment robotic navigation are the velocity obstacles developed by Fiorini, where the robot planned in the velocity space and computed the velocity that would avoid any moving agents, assuming their velocity would be constant. Also, we can find predictive approaches that use prediction of human motions to create plans for the robot that are going to avoid future collisions with these moving agents. And also, more recently, we have a work where the social interactions are detected and they are also modeled, as you can see here, and so they can be respected. So in this case, two persons talking to each other, it wouldn't be polite for the robot to pass in between them. Some problems with these approaches is that social interactions are highly dependent on context and may be difficult to detect them. For example, this man here is taking a picture of this shopping mall, and we know that it wouldn't be polite to cross in front of this man. But for a robot to detect the situation, it would be very hard because this man is alone, and only by his posture and because he's holding a camera, we can understand what's happening. Another problem of the predictive approaches is that they may fall into the freezing robot problem. The freezing robot problem has been stated by Troutman, and it says that in dense environments, due to the large future uncertainty, every path generated by the navigation algorithm may result in a collision, so the robot cannot find a solution. So to better understand this problem, there's a small video. In this video, you can see that the robot is represented by this black rectangle. It has to move from the left side to the right side of this corridor. Here you can see agents that are also moving in this environment, and these colored squares are the predicted motion of these agents. Because this is a dense populated environment, at some point all the predictions of movements of these agents are going to fill the empty space of this corridor, and in this case the robot wouldn't be able to find a solution. So the robot managed to navigate until the environment gets too dense and too crowded, and the robot cannot find a solution anymore. So it has to stop until the environment gets a bit less populated, and only then it manages to continue moving. So my proposed solution is that the robot may follow persons. So by doing this, it can take advantage of their motion in these complex and dynamic environments. The motivation for this is that the movement from persons can provide information about the environment. Humans can easily navigate in crowded and complex environments, and persons are able to deal with very complex social interactions. So as the advantages of this approach we can mention the reduction in the computational cost. The robot is able to escape the freezing robot problem that I mentioned before. Following human also kind of replicates the behavior, so it's better accepted by other humans. And also it's able to avoid undetected obstacles that persons can see but robot cannot. For example, spilled coffee on the floor. So the question is how to choose a leader. The approach used in my work is the goal similarity prediction. What happens is we have a robot here, and the robot has a goal represented by this blue triangle. We have two leader candidates in front of the robot. Based on the prediction of the goal of these two agents, for example, the yellow one has the predicted goal here, and the red one has a predicted goal in the red triangle, we can see that the red agent has a goal similar to the robot's desired destination. So in this case, this agent would be chosen as the leader. As we want to choose a leader based on the goal similarity approach, we must be able to predict the goal of the leader candidates. One form of doing this is, and the simplest one, is by extrapolating the current state of someone. So in this case we can see an agent that's moving along this corridor, and we can see in these blurred red areas the future prediction of the position of this agent. So in simple environments like this, an extrapolation of the current state of this agent is good enough to detect the future goal of this person. However, in more complex environments like this building entrance, where you have office doors, a desk and an entrance, the simple extrapolation may fail to produce a good solution because the paths are more complex. For example, here dotted lines, you can see the real path, and in different stages the extrapolation of the current state leads to positions that are incorrect for the final destination of this agent. To address the problem of goal prediction in more complex environments, we can take advantage of the fact that humans do not move at random. Instead, their motion is related to interest points, for example, office doors, entrance of buildings, reception desks, that are present in the environment. So to be able to work with these typical paths, we need to create models of it. Two known techniques are the Gaussian process and the growing hidden Markov models that are the technique used in this work. Here you can see an example of the typical paths in the environment, and here you can see the recorded trajectory of persons in the entrance of a building, and it's easy to notice that the paths are commonly traveled. This is a video of the training of a growing hidden Markov model. It's a video in fast forward mode. You can see the moving entities here are persons, and this is their real movement. And you can see the model slowly growing, where we have the nodes are states and the lines are the transitions among these states. So once the model is created, we can do the validation and show it. So what we're going to do is predict the destination of this agent. In this case, the prediction area is this represented by this red color. Here this person starts to move and we predict the goal in this zone, and once the person starts to moving, we can increase our confidence in this area. Once we have chosen a leader, we must be able to follow him or her. To do this, I used a variation of the risk-RRT algorithm, that it's an algorithm specifically developed to navigation in dynamic environments, that takes into account the probability of collision with agents and also respect the social interaction among them. Here is an example of this algorithm working. The small dots are the exploration nodes of the algorithm, and we can see where the nodes are bigger, they show a bigger risk of collision. Here we have a person moving to the left side of the corridor and another one moving to the right side. This line in front of them is the prediction of their movement. The algorithm managed to successfully predict a path that's going to avoid the collision with both persons in this situation, reducing the risk and respecting the social conventions. Once a leader is detected, its path is going to be tracked. So here we can see a representation of the robot and a representation of the leader that has been chosen. This is the leader path that has been recorded. We're going to take samples of this path and use them as sub-goals. The sub-goals are going to be used and sent to the risk-RT algorithm, so the robot is able to continue to explore the environment for alternative routes, but also to move according to the motion of the leader, effectively taking advantage of its movement. For the experiments in this work, we used simulation, and we also used simulated robot together with real data in a mixed environment of real and virtual. The GHMM was trained with both real data and simulated data. For the real data, we used fiducial markers that were worn as hats by persons, and their motion was detected by an overhanging camera. Two types of experiments were conducted in this first part. We wanted to first evaluate the capacity of the robot to detect and follow a leader, and then the capacity of the robot to avoid other persons by following a leader. In this first experiment, the robot's destination is in this. There are 3 leader candidates, and the predicted goal of the candidates is represented by a triangle. So in this case, the red candidate is chosen because its predicted goal is close to the robot intended goal. The robot starts to move, following the path of this person, and at the same time you can see the small nodes that the risk-RT continued to explore the environment. So the robot manages to successfully detect and follow a leader that's going to the same position as intended by the robot. In the second experiment, there's only 1 leader candidate in front of the robot. Again, the predicted goal of this leader is close to the robot, and we have 2 other agents that are moving in the opposite direction. By following the blue agent, the robot managed to avoid collision with the other agents properly. In the second part of the experiments, we created a pedestrian simulator based on the social force model from Helbing. It's interesting to use a pedestrian simulator because then we can take into account the reaction of persons to the presence and to the motion of the robot. Some real-life phenomena that we are able to replicate in this pedestrian simulator is the formation of lanes that occur when you have 2 groups of people moving in opposite directions, as shown in this image. This is important because the robot can take advantage of one of these lanes to move among densely populated environments. This is a video of a robot that wants to move blindly to the right side of the corridor. In this case, the robot's not going to react to the motion of the agents. But the agents, as they have been developed using this simulator, they're going to avoid the robot. This is used to demonstrate that even in the case where the robot ignores the persons, the persons take responsibility in avoiding the collisions. And also this can be used to demonstrate that the simulator is working. So some experiments that were done with this pedestrian simulator is one where the robot is able to escape a frozen situation in the same conditions that we showed in the beginning of the presentations. The robot must reach the right side of this corridor. We'll have two groups of persons that are going to move in opposite directions. In this case, you can see marked in green the chosen leader. The robot managed to switch among leaders. For example, it's going to switch from this to this again, and managed to pass this difficult situation and becoming part of a group with the moving agents that are going toward the same destination of the robot. This is a last experiment when we have three candidates and the robot wants to reach the bottom part of this corridor. The robot uses the probabilistic prediction of goal and chooses this agent as leader, starts to follow the leader's path, and as the simulator evolves, this leader is actually the responsible to interacting with other leaders, other agents, and also to guide the robot until its destination in this region. So in this work we presented a method to take advantage of the human motion. We used a probabilistic estimation to determine the candidate's goal. The leader selection was based on goal similarity. We also developed a pedestrian simulator for more realistic experiments, and tests were done with both real and simulated data. As a future work, we already started to create a new leader selection technique where we are going to use a learning framework to teach the algorithm based on human experience of what are good or bad leaders. The basic idea is that we have a camera and a laser mounted on a robot that's going to follow persons, as you can see in this image and here. And then we're going to have human users that are going to label the situations according to what they found to be a good or a bad leader. Then this information is going to be used in an AdaBoost classifier algorithm, and we hope to be able to detect and classify situations of bad and good leaders and use this information for the robot to follow them. Thanks again for watching this presentation. Once again, I'm very sorry I could not be able personally to deliver this presentation. You can ask me any questions or doubts you have using my email, procopiostein@gmail.com, and the link for this video presentation can be found in this blogspot, navigationadvantage.blogspot.pt. Thank you very much.